Welcome back to the deep dive. We've got this great stack of research papers you sent over, all focused on predictive analytics, specifically time series.
That's right. And our goal today really is to hammer out a solid blueprint for evaluation, making sure predictive models are genuinely reliable.
Yeah, moving beyond just, standard prediction, like guessing a single value into the weeds of forecasting, predicting future values over time, it's different.
Oh, it's fundamentally different.
Yeah.
And the stakes, much higher. Get forecasting wrong, and you can wreck a supply chain, blow a budget, get prediction wrong, maybe one estimate is off.
So the mission then?
Clarity. First, draw a really sharp line. This is generic prediction. This is temporal forecasting. Second, nail down the evaluation rules, the absolute must-dos to stop information leakage.
Leakage. That sounds bad.
It is bad. Leads to models that look amazing in testing but fail spectacularly in reality. And third, arm you with the basic benchmarks and diagnostics you need to choose models wisely.
Okay. And the sources cover things like visualization, time plots, ACF, this STL decomposition thing.
Yep. And the simple baselines. Naive, seasonal naive, drift, crucial stuff. Plus, how to measure success properly. Scaled errors, rolling origin cross-validation. That's the gold standard.
Got it. Let's dive in. Segment 1, the non-negotiable rules of time.
Okay.
So in normal machine learning, say, tabular regression, we often treat rows as, exchangeable, right? Order doesn't really matter for the model logic.
Exactly. You shuffle them, do random splits, stratified splits, standard practice.
But forecasting.
Absolutely not. That approach is poison for forecasting. Time order is everything. It's intrinsic. Rows are not exchangeable. Today's value depends on yesterday's, period.
You're predicting future rows based only on past rows of the same thing, demand, traffic, whatever it is.
That's the defining characteristic.
Why is shuffling so bad? If I have years of data, surely randomizing helps the model generalize.
It seems intuitive, but it causes this catastrophic failure, information leakage. If you shuffle time series data for training, your model inadvertently gets glimpses of the future.
So the training set has data points from, say, next month mixed in with last year's data.
Precisely. The model sees future events while learning from the past. So of course it looks incredibly accurate. But it's cheating. It's learned from data it wouldn't have in a real deployment.
And then it falls apart when it only sees actual past data.
Completely. That's why time-aware splits, sequential backtesting. They aren't optional. They are mandatory to avoid disaster.
Okay, rule number 1, firmly established. Don't shuffle time. Respect the sequence.
Yeah.
So how do we start understanding what's in that sequence?
We have to look. Exploratory data analysis. Visualization. If you can't see the patterns, the components, you can't model them effectively.
Starting with the simplest tool, the time plot. Just plotting the data over time.
It's fundamental. Your first step, always. It's like a fingerprint for the time series. It shows you the big picture trends, sudden shifts, outliers, seasonality.
The sources had that Ansett Airlines example.
Right. A perfect case. The plot immediately showed, boom, 0 passengers for a period. Why? Industrial dispute in '89. Couldn't miss it.
And another dip later on.
Yeah, a less drastic drop in '92. Turned out they were doing a trial seat replacement. Again, an external event impacting the pattern, visible right there on the plot.
Which tells you you might need models that can handle these kinds of external shocks or interventions.
Exactly. Or at least you need to be aware of them when interpreting your model.
There was also the Australian anti-diabetic drug sales data.
Another great example. Clear upward trend, definitely, but also this really strong seasonal pattern. Sales dipped sharply right at the beginning of each year.
Not just random noise, though.
No, not at all. It was directly linked to government policy. Patients were encouraged to stock up before the end of the year for benefit reasons. So that sharp dip wasn't some complex cycle. It was a fixed, predictable seasonal effect driven by policy.
If you just looked at the numbers, you might miss that context.
You might. And you might try to fit a complex model to something that's actually quite straightforward once you understand the driver. This leads us to defining the key components we often look for.
Okay, what are they?
Generally, we think about trend. The long-term, sustained increase or decrease. Is the series generally going up, down, or staying flat?
Makes sense.
Then seasonal. Patterns that repeat over a fixed known frequency tied to the calendar. Yearly, quarterly, monthly, weekly, even daily cycles, like retail sales spiking every December.
Okay, fixed frequency is the key for seasonal.
Absolutely, which distinguishes it from cyclic patterns. These are also rises and falls, but they're not of a fixed frequency. Think broader economic cycles, booms and busts, often lasting multiple years, maybe 2 years, maybe 10.
So the core difference, seasonal is fixed calendar period, cyclic is variable period.
You got it. Recognizing which you're dealing with is crucial for model choice.
Beyond just looking at the plot, there's the autocorrelation function, the ACF. How does that help?
The ACF is a powerful diagnostic. It measures how strongly observations in the series are related to observations at previous time steps, or lags.
So how does a trend show up in the ACF plot?
If there's a strong trend, the autocorrelations for the first few lags, lag 1, lag 2, etc., will be large and positive. And crucially, they'll decrease very slowly as the lag increases. It's like the series has a long memory because of the trend.
Okay. And seasonality.
That shows up very differently. You'll see significant spikes in the ACF plot, specifically at lags, corresponding to the seasonal frequency. For monthly data with yearly seasonality, expect big spikes at lag 12, lag 24, lag 36.
Because this month is strongly related to the same month last year and the year before.
Exactly. It's a clear signature.
What if there's no pattern? Just random fluctuations?
That's called white noise. In that case, the ACF plot should show virtually no significant autocorrelations. All the correlation values should be close to 0, basically bouncing around randomly within the confidence bands.
Those dashed lines you usually see on the plot?
Yep. For white noise, roughly 95% of the spikes should stay within those bounds. And $1.96 Chorister T, where T is the length of the series. If you see spikes consistently breaking out, especially at specific lags, you know there's structure there to be modeled. It's not just noise.
Okay, so we've used CLOTS and ACF to diagnose the patterns. Now, how do we formally separate these components? Trend, seasonality, remainder?
That's where decomposition methods come in. The first choice is often between an additive model or a multiplicative one.
What's the difference?
Additive assumes the magnitude of the seasonal fluctuations is roughly constant, regardless of the overall level of the series. Think 100S plus T plus R watt. Sales go up by about 1,000 units every December, whether total sales are 10,000 or 50,000.
Okay. And multiplicative?
Multiplicative assumes the seasonality scales with the level of the series. Think wet M is composed S times T times RR. Sales go up by, say, 10% every December. So if sales are 10,000, the increase is 1,000. If sales are 50,000, the increase is 5,000. The percentage is constant, but the absolute amount changes.
So multiplicative makes sense when the variation grows as the series grows.
Exactly. And a popular, quite robust method for doing this decomposition is STL seasonal and trend decomposition using LOES.
Why is STL considered good?
It's very flexible. It can handle seasonality that changes over time, which is common. And importantly, it has a robustness option. This means outliers, like that Ansett strike, mainly just affect the remainder component and don't distort your estimates of the underlying trend and seasonality.
That seems really useful, and the output we often want is the seasonally adjusted data.
Often, yes. That's the original data with the seasonal component removed in the additive case. What's left is the trend cycle combined with the remainder, trends RTO. It helps you see the underlying movement without the predictable seasonal noise, useful for analysis beyond just forecasting.
Okay, so we understand the data structure. Now, before we jump to complex models, we need benchmarks, the forecaster's toolbox of simple methods.
Absolutely critical. These are the methods your fancy model must beat. If it can't, why bother with the complexity?
What are the main ones?
There are 4 core benchmarks usually considered. First, the mean forecast. Just predict the average of all your historical data. Simple.
Okay.
Second, the naive forecast, also called the random walk forecast. This just is the forecast for tomorrow is whatever the value was today. YRT plus etcetera YP2. Surprisingly effective sometimes.
Just repeat the last value. Got it.
Third, the seasonal naive forecast. If you have seasonality, this predicts the value will be the same as it was in the last seasonal period. So for next quarter, predict the value from the same quarter last year. YODT plus 8 plus HADC, where HUM is the seasonal period.
Makes sense for seasonal data.
And fourth, the drift method. This takes the naive idea but adds a trend. It draws a line between the first and last observation and extrapolates that line forward. Essentially, it forecasts the last value plus the average historical change per period.
So these 4 are the basic litmus test.
Precisely. They set the floor. If your sophisticated model can't outperform the relevant simple method, often naive or seasonal naive, then it's probably not adding much value. Or worse, it might be overfitting.
The sources use that Australian quarterly beer production example. Very seasonal data.
Yes. And when they tested these simple methods on the data after 2006, what happened? Mean was off. Naive was off because of the strong seasonality. Drift couldn't capture the seasonal peaks and troughs properly.
But seasonal naive?
It did pretty well. Because the dominant pattern was the quarterly cycle, simply repeating the pattern from the previous year was a strong baseline forecast. Hard to beat for that particular series.
Which brings us perfectly to evaluation. How do we measure if our model is actually better than, say, seasonal naive? We know looking at residuals, the in-sample fit is misleading.
Dangerously misleading. Residuals are calculated on the data the model already trained on. Of course, the fit looks good. It doesn't tell you how well the model will predict new, unseen data. You need genuine out-of-sample accuracy.
Okay, so we need out-of-sample metrics. Lots of people default to MEE, mean absolute percentage error. It seems intuitive, right? Percentage error sounds easy to understand.
It sounds easy, but it's problematic in practice, especially in areas like demand forecasting.
Why? What's wrong with MAP?
Two major flaws. First, it blows up, becomes undefined if the actual value is zero. Think about forecasting sales for a product that sometimes has 0 sales days. MAPE breaks.
Okay, divide by zero error.
Right. And it also becomes unstable and gives massive percentage errors if the actual value is very close to 0. Second, MAPE has an asymmetry. It penalizes forecasts that are too low, negative errors, more heavily than forecasts that are too high by the same absolute amount.
Really? I didn't know that.
Yeah. So if you optimize for MEE, you might inadvertently bias your forecast to be slightly higher than they should be. For intermittent demand or low-volume items, MAPE can be really misleading.
So if not MAP, what's a recommended alternative?
Scaled errors, specifically MAC, mean absolute scaled error, or sometimes RMSE, root mean squared scaled error.
Why are they better?
Key advantages. 1, they are scale independent. This means you can compare forecast accuracy across series with totally different units or magnitudes. Apples and oranges comparison becomes possible.
Okay, that's useful.
2, they explicitly compare your model's error against the error of a benchmark, usually the naive model, specifically the average absolute error of the one-step naive forecast on the training data.
How does that help?
It gives the error context. The scaling factor is the average error of the simplest possible forecast. So the resulting FV score has a beautiful interpretation.
Which is?
If your Macy's is less than 1, it means your model's average absolute error is smaller than the average error of the naive forecast on the training set. You beat the benchmark.
And if it's greater than 1?
Your model is doing worse than just repeating the last value. It's a clear, interpretable hurdle. Macy 1 is good, Macy 1 is bad.
Okay, ME sounds much more robust than MPE. But how do we calculate this ME score reliably, avoiding that in-sample trap?
Through the gold standard evaluation protocol, rolling origin cross-validation, sometimes called time series cross-validation or evaluation on a rolling forecasting origin.
Rolling origin. How does that work differently from standard K-fold CV?
It strictly respects time order. Imagine your data stretched out on a timeline. You start with an initial chunk of data as your training set, let's say the first year.
Okay.
You train your model on that first year, and then you forecast the next period, say, the next month or quarter. That's your first test set. Crucially, the test set contains only data points that occurred after the training set.
No leakage.
0 leakage. Then the origin rolls forward. You add that first test period's actual data to your training set. So now your training set is year 1 plus month 1.
And you forecast the next month, month 2.
Exactly. Train on year plus month 1, test on month 2, then roll again. Train on year plus month 1 plus month 2, test on month 3. You keep rolling forward, generating a series of forecasts on genuinely out-of-sample data.
Mimicking how you'd actually use the model in real time.
Precisely. It simulates the process of periodically retraining your model as new data becomes available.
The sources use this for Google stock prices, right? Looking at multi-step forecasts.
Yeah, they used it to see how accuracy degraded over, say, an 8-day forecast horizon. And guess what? The error reliably increased the further out they tried to predict.
Which makes intuitive sense. Predicting tomorrow is easier than predicting next week.
Of course. And the rolling origin CV setup allows you to measure that degradation properly. The sources also hammered home the point. Compare the error metrics from this rigorous CV process to the error metrics calculated from simple in-sample residuals.
And the CV errors will always be higher or look worse.
Almost certainly, because the residuals benefit from having seen the entire dataset during fitting. The rolling origin CV errors give you the honest, realistic estimate of how your model will perform on future, unseen data. That's the number you should trust.
Okay, this seems like the complete picture now. We diagnose with plots ACF, decompose with STO, benchmark with simple methods, and evaluate rigorously with NANIC calculated via rolling origin CV. How does it all come together in a workflow?
A common and effective strategy combines decomposition with forecasting. You first decompose the series into seasonal, trend, and remainder components, using SDL for instance.
Okay.
Then you forecast the components separately. For the seasonal component, since it's often quite regular, you might just use a seasonal naive forecast. Assume the seasonal pattern repeats.
Makes sense. And the other part?
The other part is the seasonally adjusted data, AT plus RTA. Since the predictable seasonality is removed, you can forecast this using a non-seasonal method. Maybe it's just naive, maybe drift if there's a trend, or maybe a more sophisticated non-seasonal time series model like ETS or ARIMA.
And then you just add them back together.
Exactly. You combine the forecast for the seasonal component and the forecast for the seasonally adjusted component to get your final overall forecast.
Yeah.
Forecast CNE times, forecast betas, then add them up, or multiply if using multiplicative decomposition. It's called reseasonalizing.
We saw how crucial this careful evaluation was in that synthetic data example. 400 days, clear trend, 75-day seasonality.
Right. They compared 3 models: simple naive, FETA, which focuses on trend, and ETS, exponential smoothing, that explicitly models both trend and seasonality.
And they used rolling origin CV.
Yep. A proper setup, 180-day initial training window, forecasting 30 steps ahead, then rolling the origin.
What were the results? Did the complex model win?
Absolutely. Naive had an average MAPE around 0.285. FETA, despite being trend-focused, was actually slightly worse at 0.297. It likely struggled with the strong seasonality.
And ETS?
ETS, which was designed to handle both the trend and the seasonality present in the data, achieved a mean MAPE of just 0.051, a massive improvement.
Wow, so the complexity paid off, but only because it correctly matched the patterns diagnosed in the data.
Precisely. And the rolling origin CV provided the undeniable quantitative proof of that lift. Without that rigorous test, you wouldn't know for sure if ETS was genuinely better or just looked good on paper.
So the final word on model selection.
It's simple. Choose the model with the lowest forecast error, preferably measured using MANSI or RMSSC, calculated using time series cross-validation, like the rolling origin method. That's the most reliable path.
Let's recap the essentials then.
Okay, the 4 non-negotiables from this deep dive. 1, forecasting demands time-ordered, leakage-free evaluation. No shuffling. 2, always set a benchmark. Naive or seasonal naive are your starting point. Your model must beat this.
3,
Use scaled errors like MS or RMSSE. They're scale independent and give you that direct comparison to the benchmark, superior to MAP for robustness. And 4, rolling origin cross-validation is the only way to get trustworthy out-of-sample error metrics for model selection.
perfect. So here's the final thought I want to leave everyone with, drawing on all this material. We've seen simple methods like naive and seasonal naive can be surprisingly tough to beat.
Often they are, yes.
Yet more advanced methods like ETS clearly can provide significant improvements, but typically only when there are clear patterns like trend and seasonality that they are specifically designed to capture.
Right. The complexity needs a purpose.
So the question for you is this. If you build a complex forecasting model, maybe with dozens of features, tons of engineering, and it fails to significantly beat a simple seasonal naive forecast when tested with rigorous rolling origin cross-validation, is that complexity actually doing anything useful?
Or is it just, as you said, sophisticated guessing?
Exactly. Is it adding genuine predictive power or just adding opacity and potential for overfitting? The takeaway here is always demand that quantitative proof of lift validated through proper time series CV before you abandon the power of simplicity.